So the effect of dissolved solids in a solution on boiling point is that it raises the boiling point, notice the word elevation, and it lowers the freezing point. So if you're looking at one of those heating curves, so like you see that happening at 0, and then that happens at 100. So that's your normal ranges. Basically what it does, I like to put like my hands out here. So like there's my hands, and then when you have a solution, it raises that up and it lowers it down. So the curves change, and this part of the problem, instead of it being at 0, it's going to be at a lower value. And it actually changes the range. It kind of makes it be a liquid in a range a lot longer, is kind of what it ends up doing. And I'm going to take the top part and move it up. There you go. So see how that's a much larger range than what we originally had. So it goes like from there. So I like these because you can always kind of check your answer. If you get an answer and it's under 100 and you're looking for how the boiling point changed, you did something wrong, because it's got to be above 100. And same thing for their freezing point. If you get an answer and it's above 0, you did something wrong, because it's got to be below 0. That's what it does. And then we got a picture over here that's kind of helpful too to help understand it. So this is temperature, right? So this is the pure solution right here. So we're saying that at this temperature, and if we like stay at a constant pressure, let's just say the pressure is like right here, and we go across, so the solid, and notice that we hit the phase where it begins to turn into a liquid sooner than when we have the pure substance. So that makes sense, because it's at a lower temperature that it begins to become a liquid. That's the range. That's basically how the freezing point is changed. And then if we keep going across, so this is where the pure thing would be, and you can see that the pure boiling point goes way out. Sorry that my line is not beautiful, but so this is like the solution, and then the thin ones are the pure ones. So you can see the range is wider. You got a wider liquid range and narrower solid. And I don't know that you would say a nearer. I mean, gases have quite the range. So the way I like to learn this, I don't like to learn twice as much as that I don't need to. So I learned the generic equation: the change of temperature is equal to the K times the molality. Now in a minute, I'm going to add another term for this, and it's the I term. But for right now, I'm just letting you know, so just not surprised. We're going to make a little change to it in a bit. It's a really easy change though. It's just like a whole number that you might add in some of the time. And if the problem is talking about boiling, well, then I throw some B's in here and I use those numbers. If the problem is talking about freezing, I throw the F's in there and I use those numbers. So I like the generic form of it. In this case, you can read about it. It wants to know the new freezing and the new boiling point. So we're going to need some of each of them. Nice enough. It's already given us the molality. And then we have to use our own information. If it's added to water, we know that the freezing point of water is 0. And we know that the boiling point is 100. So I'll just do the freezing point one on one side, and I'll do the boiling point one on the other side. Here's another trick: is instead of trying to break this down into TI and TF and like move the T's and everything around, you may have seen me do this on the delta T equals MC. Sorry. Q is equal to MC delta T. When you have to solve for delta T math-wise, you make less mistakes if you just solve for the quantity delta T and then you plug in and solve for whether it's the final or the initial. So I'm going to be solving for the delta T in both cases. It's especially helpful in this because it's really obvious to add or subtract. Okay, so that's equal to that times my KF or my KB. This is my KF. And then delta T equals M times KB. So you'd have to be given these values. So the KF value is 1.86 degrees Celsius per molality, and the KB value, this is for water. If we were talking about something else, it would be different values. But the KB value is 0.152 degrees Celsius per molality. I want to throw something else out there. These equations have K's in them. There are other things in our chapters coming up that have K's. So there's a little k coming up when we talk about rates, and there's a huge k that comes up in almost every single problem when we talk about equilibriums, KAs, KBs. So heads up, that's not the only time you're going to see a K. Just know that you use these Ks in the context of just the boiling point elevation, the freezing point depression. All right, so we just take our molality, 0.33 molality, times our Kf value, which is at 1.86 degrees Celsius per molality. Notice our molalities cancel. And that gives us, actually, I'm going to fill the other one in too. Delta Tf is equal to 0.33 molality times 0.512 degrees Celsius per molality. So the molalities cancel. So now I can solve for both of them. That's supposed to be Tb. Tb, that's Tf. So 0.33 times 1.86 gives me 0.6138. Notice that I've got 2 sig figs, so I'd round that to just 0.61 degrees Celsius. That's my change. I'm not done with the problem yet. 0.33 times 0.512. And again, I've got the 2 sig figs, so 0.17 degrees Celsius. And so that's 0.61 degrees Celsius. That's my change. Now I got to remember, what's my original boiling point? Well, my original boiling point was 1, and it goes up. So my new boiling point is 100.17. These actually can affect boiling points quite a bit. Like it can change it up to 5 and whatever. These are just workable numbers for one example here. So don't discount it. And then the freezing point, remember freezing point goes down. So 0 minus 0.16. And so my number is going to be negative 0.61. So in these problems, I would just recommend be really careful on what you're reading. Most of the time, you aren't solving for TF, delta TF, or delta TB. You're actually solving for the final boiling point. So you have that extra step in there.